Hello, this is Paul from Foresight Tech. In this video, we are going to deal with the derivative of natural exponential functions. And here you can see, and we will have the first definition for what is E. I think you know what is E already, right? E is we call the natural number. When you learn exponential functions, we have the natural exponential function. The base E we call the natural number, or we say is Euler number. And I think you can find the approximation in your calculator, right? Like 2.718 to A1A2A, like that is a irrational number. Okay. And this is very famous, the number, okay, as famous as pi, okay, and the history is super important. And you also know, and Euler is one of the best mathematicians in the history, right? Okay. And here we give the first definition, how to define E. And here the definition, E is the number such that this limit equals 1. It's very strange why we have this limit. Okay, so I will going to introduce later. So suppose if this limit equals 1, that's equation, right? So this equation we can find the number E. That E we call the Euler number. That is the first definition of Euler number E, or natural number E. And what does this limit mean? Okay, this limit just means if we define E in this way, and then E is a number, of course a real number, is an irrational number, and then E raised to the x, we call the natural exponential function. And then this function has a slope of 1 when x equals 0. Okay, and the next slide I will show a graph to explain what that does mean to you. So first, if we have the definition, can we see how about the slope is 1, and this limit exactly is the slope. Okay, is the derivative of ex at 0. Why? We are going to look at it. And the slope is the derivative. If we look at derivative of 0, and we use the definition, right? Okay, so then we plug ex to f, and this one should be 0 plus h, of course is h. F at h is e raised to the h's power, minus f at 0. F at 0, e0 is 1, definitely, right? And then over h, can you see? That's exactly the limit in the definition. Okay, so this definition is 1, therefore is already 1. And therefore derivative is 1 at x equals 0. What does this really mean? Can we look at the graph? Okay, so here we have a graph. So you can see, we look at the left graph. We deal with the exponential function. So we have 2 exponential function. The first, the blue one is y equals 2 raised to the x power. The black one, y equals x raised to the x power. So can you see the base are different? Okay, of course the curve are different, right? And the 3 raised to the x raise up to infinity much faster than y equals 2 raised to the x power. That's going to look at the derivative at x equals 0. Okay, if we draw tangent line, draw 2 tangent line, or you just going to find the derivative or find the slope of the tangent line at 0, we will have these results. Okay, the tangent line for the blue one, y equals 2 raised to the x, is less than 1. And the tangent line, the slope is greater than 1 for 3 raised to the x power. What does it mean? Okay, from a less than 1 to a greater than 1 number in the middle, we should have another exponential function has the derivative equals 1. Okay, that's what we define. If the derivative is equals 1, like this pink one, we call the y equals e raised to the x. You know what is e, we just defined, use the limit, right? Okay, this is the basic exponent. So we should find e so that the derivative is 1, because the derivative is between -1, between a number less than 1 and a number greater than 1, okay, because of the continuity. So you can find a 1, okay, in the middle. Of course, you also can see we have a basic number or value for e. See, the base e should be between the base 2 and the base 3. Do you remember the definition for e? It's 2.71828. 2.7 exactly is between 2 and 3. All these are consistent, okay? And we say the derivative equals 1 at x equals 0. Can you look at the right? If we only look at y equals e raised to the x power, this we call the natural exponential functions. Can you look at here? Okay, we just proved that the derivative is 1, right? Therefore, the slope is 1. Okay, so which means this function is very good. We call the natural exponential. But this is not the most important. The most important is here. Okay, so can we look at it? We take any point. We're going to find the slope. Do you know what is the slope? The slope is e raised to the x power. What is? And the slope just equals itself. Okay, and when the point goes up, which means what? Which means y goes up and then the slope goes up. Can you see this? Okay, and this is the most important properties for the natural exponential functions. Why we call it this is natural? Because the derivative at any point equals the y value of itself. Okay, so the most important property. And let me going to summarize that property we just discussed here. That means what? Okay, means the derivative equals the self. Okay, that's the derivative equals the self. If we have this rule, I have one I have to show you. In the future, you will learn. And if any function take a derivative equals itself, and that function, the only choice for that function is the natural exponential function. Okay, that's a very strong result. Okay, in the future, we were going to show you. Or if you're going to differential equation, and then we were going to show you. And then in Calculus 2, you also will learn that results. Okay, and now we have a remark. So we put the word, if we know the first derivative equals itself, how about the second derivative? Okay, the second derivative is the derivative of the first derivative. Can you see? The first derivative is e raised to the x. E raised to the x, take a derivative again, of course, is itself. Therefore, the second derivative is still itself. The same, the third derivative is itself, right? The fourth, the any nth derivative, all equals itself. So strange, right? It's the only functions that you know. We call it exponential, natural exponential functions fit for this property. This is very, very, very good property, okay? And in the future, for any other exponential functions, you know, if we change the base, and then of course we have another exponential now called the natural exponential. And the derivative for that kind of exponential function, so we have to use these results in the future. I have to wait. We have to wait until we learn the chain rule in the future. Okay, the future chapter we have another tool we call the chain rule. If you learn chain rule and then you come back and they combine these results, you will definitely have the derivative for all the exponential function, no matter the base is a natural number e or not. And now we give a proof. So how to get this exactly? But we are only proved, you know, is natural exponential function has derivative equals 1 at 0, right? But how about the derivative function? which means this formula. So all we need to do, look at it here. All we need to do is use the definition. Okay, dividable function is this, right? That's the definition. And then we plug this f at x plus h is e raised to x plus h minus f at x, which is minus e raised to the x power. Okay, so that's the definition. Now what do? We use the product rule. Okay, e raised to x plus h separated, we have e raised to the x power times e raised to the h power. Okay, and then we look at e raised to the x minus e raised to the x. So this is the common factor. We factor out. We're going to here. Okay, and then what? And then we look at e raised to the x. Okay, so if x is a fixed number, e raised to the x is a fixed number, has nothing to do with the limit. Okay, has nothing to do with h. Therefore, and this is just like a constant number. Okay, what do? We use the limit law. We can just factor this constant number out. Therefore, we're going to here. Can you look at this red one now? What is? That's one. Why? That's the definition for e, right? In the definition for e, we said that this limit equals 1. So therefore, we have this e raised to the x power times 1 equals e raised to the x. Therefore, natural exponential take derivative equals the natural exponential, which is itself. We proved that these results. That you know. Now, all we need to do is just use the results. Okay, so we're going to practice 2 questions and the simple questions we're going to do. Look at these questions. E raised to the x, that's what? That's a natural exponential function. And then we're going to take a derivative equals to itself. How about the x? X is a power function, take a derivative. We already know x take a derivative is 1, right? So how about the linear combination? This function is just the linear combination of natural exponential function and the power function. What to do? Linear property. Do you remember last topic we did? Linear property to do. Okay, so let me show what I can get. All we need is just do this. All we need to do is just use the linear property, right? Okay, so let me see. We call the linear property. Do you remember this? Okay, and then we can get everything. Okay, so we use the linear property. Now we have this, the derivative for y. Okay, take a derivative. The derivative goes to the first function f, the second function g, which means 2 parentheses e x parentheses take a derivative plus parentheses x take a derivative. Can you see? Okay, the coefficient does not matter. Okay, so now what do? You know, right? The derivative of exponential, natural exponential is the self. Therefore, the first is 2ex. What the second? The last time we did, which is 1, right? Okay, plus 1. This is already the results. Let's look at one more. Can we see these questions? Okay, so this time is different. Okay, someone you know, and what is this is a composite function. Okay, is a natural exponential composed with the linear function. We don't have the chain rule to find the derivative of the composite function, and which is the future topic. Okay, I will going to show you later. So far, how to do? You can imagine doesn't look as not a linear combination. Okay, but it is. If you remember the sum you plus, you can expand by the product rule. If you can expand this by the product rule, then you will find that this is just like the first questions. This is what? This is a linear combination. Okay, so let me give the idea. All we need to do is the similar. Expand. Okay, we expand this into a linear combination. Okay, how do you expand? Sorry, how do you expand? We just do the very similar as the first questions we did. So we do this: y equals e, the first one's power, times e raised to the x power, and then plus 1. Can you see what that does mean? This is a product of the rule, and the first power is 1, second power is x. If we add them together, is x plus 1. We just go backwards. Okay. If we look at this now, do you know what this is? A linear combination. So e raised to the x power is a natural exponential function. 1 is what? Is power function, right? Or constant function, whatever. Okay, so now it's a linear combination. We can use the linear property. Okay, now easy. We do what? Let me show you. So here, what we can do now? We can use the linear property, or someone you know is a linearity, right? So if I write linearity, is the same. Okay, so y take a divided should be equal to what? Constant number does not matter. Parenthesis, and this take a divided, right? And then plus 1. Okay, if you like it, you put a parenthesis, no problem. Take a divided. Okay, so this is the linear property. And then what to do? And this is itself, right? So we have e times e raised to the x. And you know what this? How many? 0, right? Constant number take a divided is 0. And we can simplify later. And this is a product of the rule. We take it back. See, is still go back to e x plus 1's power. Ignore the 0. This is the result. Okay. That's all. Thank you. Let me go back. And if you have any question about this topic, please leave your comments. And if you like this video, please subscribe to my channel for more videos. In the next video, we are going to deal with so you can see here, we are going to deal with the derivatives using product rule. Okay, we are going to deal with product rule. That's all. Thank you. Have a nice day. Bye.